Welcome dear participants to the second part of experiment number 13 for section A IAVOC 105 coursework. Here in this part we will be working on DeMorgan's theorem. There are two theorems given by DeMorgan. You have already gone through this in your theory coursework. You can see that DeMorgan's first theorem states that if we have two or more number of variables and we perform an AND operation, of the variables and we take their complement. So first we have to perform the AND operation, then we have to take the complement or negation of that. That quantity will be equivalent or equal if we take the complements of same variables and we OR them. So here you can see the two variables are A and B. Here the two variables are A and B again. Here we have performed the AND operation of the variables and we have taken complement of that. And here in this side, on the right hand side, we have taken complement of A and complement of B. We have taken OR of them. These two will be equivalent. This is DeMorgan's first theorem. And DeMorgan's second theorem is just opposite to that. If we have two variables in this case, A and B, we have taken their OR operation. After the OR operation is over, we have taken the complement or negation of that. It is equivalent to AND operation of the individual complements of A and complement of B. So these are the two theorems given by DeMorgan, which helps in simplifying digital circuits like anything. Already you have gone through this theorem in your theory coursework, and at the same time I have given adequate theory in the manual. So we will directly go for doing the experimental part. Now you can see that for this we will be using Omega Mech type LTB 818 trainer. Right, this is a very comprehensive trainer to prove each and every law of Boolean algebra as well as DeMorgan's theorem. Let us try to understand what is there in this. This is again a kit. I will go for the video mode. This is again a kit which is actually driven by AC supply. You can find here. This is the AC supply. Okay, you can see. And after making necessary rectification and lowering down of the AC power, it is converted to DC 5 volt level, because this is a digital circuit that we are going to make. This is the power on off switch. These are the three switches that give logic input to the gates. Now you can see these are the three variables: variable A, variable B and variable C. Okay, now the board gives us three different type of gates: NOT gate, AND gate and OR gate. You can see this is the block of NOT gates. You have got 4 NOT gate, individual NOT gates. Here you have got 3 individual AND gates. Each of the AND gate are having 3 inputs, and this is the OR gate block where you have got 3 OR gates. Each of them are individual, each of them are having 3 inputs. Okay, so this is all about the trainer. Fine, you have got 2 LEDs, okay, for verification of the output status. The LEDs are connected through an 220 ohm resistance to ground, so that excessive current cannot pass through it. And again, anode of the LEDs are kept open, so that the anode can be connected directly to the output of any of the gate. Now here there are definitely logic ICs that are used in the circuit as gates. That logic ICs and their circuit are inside this trainer that we cannot see. For the sake of our understanding, only these diagrams or the schematics of the gates have been given on the experimental panel. Now this experiment can definitely be performed using breadboard or the breadboard trainer that we have seen in our earlier session. But we have to remember that in that case, number of watts will increase like anything, and definitely it will become very hard to follow in the video the every part of the circuit through that breadboard connections and all. Therefore, we have used this specific circuit for this demonstration purpose. Now what I will do, first of all, I will connect these three inputs to the AND gate inputs. Let us do that and see whether the AND gate operates as per the truth table that we have already studied. So I have connected it here. I have connected it to input 1 of the AND gate. Next, I will take this input, that I will connect to another input of the AND gate, and I will connect the third input to this input of the AND gate, and I will straight away connect okay, fine, I will use the second AND gate for my purpose of easiness. Okay, right, I have done the same thing. You can see the three inputs are connected to three inputs of the AND gate, and here you can find this output. I am connecting it directly to the LED. Now I will put the switch on. You can find the output is high. Why it is high? You can see very easily that all the inputs are right now in high condition. I understand that this will be a problem for your visual understanding. All these three switches are in their high state. Therefore, the output is high. Now, if I make any of them low, you can see the output becomes low. This is very obvious because an AND gate requires all of the inputs to remain in high state in order to have an high output. Okay, so this we can verify within just our Tinkerhead. Now you can see I will add one NOT gate after this AND gate, because what the DeMorgan's theorem requires? The DeMorgan's theorem requires that you have to first execute the AND operation with the variables, and then you have to take their complement. Okay, so in order to have this complement, I will disconnect the LED from the circuit. I will have the output of the AND gate. You can see this is the output of the AND gate. This is connected to one NOT gate. Okay, this is connected to one NOT gate, and output of the NOT gate finally is connected to the LED. Okay, now you have to focus on this LED and the status of this three switches. So at this condition, you can see all of the switches are high. All of the switches are in high status. If it had been simply the output of the AND gate, the output should have been high. But here in this case, you can find it is low. Now, if I make any of the switches low, you can see you have an high output. Now let us try to follow the truth table. Let us go for the truth table for verification of DeMorgan's first theorem. You can see here that if all of the switches are low, the output should be high. However, when all of the switches are high, the output is low when we are considering the negation of the AND operation. So only in one condition the output is low, that is when all the inputs are high. However, for all of the rest of the situations, the output is high. So let us try to see that through our experimental operation. Right at this position, you can see all the outputs are high because I have kept none of the switches in pressed condition, so the output is low. You can see the output is very much low. Now let us try to make any of them low. Okay, it is high. I will make the other low. It is high. I will make the other low. It is high. Now I have to make any two low. So you can see these two switches are in low condition. This is in high condition. The output is high now. Now I will make this high. I will keep these two in low condition. You can see the output is high. And I will make all of them low right now. You can see the output is high. So here I will get back to the truth table. You can see for all of them to be in the low condition, the output is high. When any one of them, you can see any one of this is C is high, in this case B is high, in this case A is high, all of them the output is high. Okay, so here you can see the very simple condition is the output will be low only when all of the inputs are high. You can see all the inputs are high, the output is low. For any other condition, the output is high. So you have already seen that. So this is proving this column, this particular column, where we can see the last but not one column, A, B and C, AND operation has been performed on them, negation has been done. So we have seen that it is valid. Now we have to make complement of 3 variables, and then we have to go for an OR operation. Okay, so that we will do now. We have to first make complement of A, then complement of B, and then complement of C, and finally we have to OR them. Let us do that. I will dismantle this. I will take out the connections. So now what I will do, you can see I will take the 3 inputs as usual. Okay, I will connect it to one NOT gate, another NOT gate, and definitely another NOT gate. So now you see here what is the condition. Input A, input B and input C, they are given to the inputs of these NOT gates. So when I will take output of these NOT gates, what will happen? We will be getting complement of A, complement of B and complement of C. So here complement of A, complement of B and complement of C. So those complements I have to connect to the OR gate. You can see this is an OR gate. This is a 3 input OR gate that I am using for this experiment. This is my choice. I will this OR gate. I will take this OR gate, and output of the OR gate I will be connecting to the LED. So this makes your circuit completely ready. I will put it on, and now you can see when all the inputs are high, you can see at this position all the inputs are high. Okay, output is low. If any of the input is low, you can see the output is high. I will make this low, or I will make this low. Okay, now let us go for combination. I will make this 2 low. In the next proposition, I will make this 2 low, or I can make this 2 low. In any case, it is high. When all of the inputs are high, then only you can find the output is having a low status. Let us get back to the truth table. You can see when all the inputs are high, then only the output is low. You can see here, in this particular case, all the inputs are high. So the output is low. For any other case, you can see the output condition is high. We have already seen it. We can take any random test. You can see 2 of the inputs are high, a low, the output is high. I can take any random one, it is low, the output is high. So our DeMorgan's theorem 1 has been very easily proved. We have built the circuit and have verified that yes, DeMorgan's first theorem is very much correct. Now we will go for DeMorgan's second theorem. Let us go for the circuit first. So you can see here, this is DeMorgan's second theorem. So what they have done, we have to take the OR. We have to take the OR because let us go for the statement. What is the statement of DeMorgan's second theorem? Yeah, we have to take OR of the two variables first, and then we have to take AND of each of the complement of the variables. Definitely after doing the OR operation we have to take its complement. So accordingly we will build the circuit. Here is the circuit, you can see. We will try to understand the circuit first. What they have done, these are the three inputs A, B and C. Just we had performed with an AND gate. Here we have to perform the OR operation first. We have to perform the OR operation. After the OR operation is over, the output has to be complemented. Okay, therefore this NOT gate has been used. The output of the NOT gate is connected to an LED. Now you see here on the other hand, we will have this AND gate. We will have this AND gate. Now before doing the AND operation, we have to take complements of each of the variables. So you can see the NOT operation of A, the NOT operation of B and the NOT operation of C has been performed, and after that their outputs, that is the complements of A, complement of B and complement of C, they are fed to one AND gate. This is a 3-input AND gate. I have fed it to the AND gate and output of the AND gate is directly connected to the LED. So this is all of the circuit. Let us now try to build the circuit. Okay, so we will put the power off. We will dismantle whatever there was on the board. Okay, so you can find that these are the three inputs. Fine, I will be doing from 0. So you can see these are the three inputs. I will be putting these three connections over there. Now you have to get back to the circuit diagram. The three inputs are being fed to an 3-input OR gate. Okay, so you can find this is the OR gate input 1, OR gate input 2 and OR gate input 3. Okay, so this has been fed to the 3 inputs of the OR gate. Now let us try to verify the operation of a simple OR gate. What does an OR gate state? An OR gate state that the output will remain low only when all inputs are in low status. For any of the input that is high, the output will be high. So we can see over here, okay, you can see that all the inputs right now, they are at logic low. I have pressed the switches, they are at logic low, therefore you can see the output to be low. If any of the logic is high, you can see the output is high. I will make this high, you can see the output is high. I'll make them high, you can see the output is high. So you can see that the OR is perfectly operating. Now what we have to do, we have to take a complement of this OR. ये जो OR function है उसका एक complement हमें चाहिए. So for that I will be getting one NOT gate into our circuit. You can see I will take in this I will take this last NOT gate for easy visibility. The input of the NOT gate is connected to the output of the OR gate. Okay, and then you can find that the output of the NOT gate is connected to the anode of the LED. Now you can see, first I will keep all the switches in high condition. Now you had seen that when we were talking about simple OR gate, when all the inputs are high, the output used to be high, but here the output is low. Now I will make any of the input, logic low. You can see it is not working. I will make this logic low. It is not working. I will make this logic low. Now you can see it is high. So this is exactly the opposite operation to that of an OR operation. Why it is happening? Because we have connected this NOT gate. We have simply connected this NOT gate at the output of OR, and the output of NOT gate is connected to the LED. Fine. So let us get back to the truth table. You can see here, only when right now we are in this operation, we have complemented each of the variables. We have complemented A, we have complemented B, and we have complemented C. Now after the complements have been taken, OR operation have been performed. OR of A complement, B complement, and C complement. So this OR operation have been performed right now. So you can see here, only when all the inputs are low, the output is high, and for any other case the output is low. You can find here very easily, all the inputs are low, then only the output is high. You see the last column. For all of the conditions of the other conditions of the input, the output is low. So you have already seen it. Still you can see the LED is at high status. The LED is at high status. All the inputs are at low. This is low, this is low, and this is low. You can see the inputs are low. Okay, so the output is high. Now if I make any change in that, the output is low. So that means very easily that if any of the output is high, input is high, then you can find the output is simply low. So this is the condition of the last column, that is this column. Now we will go for this column. For that, what we have to do? We have to make OR operation with A, B, C. A, B, C, we have to perform an OR operation with them, and then we have to take a complement. Okay, so let us do that. I will go for this particular circuit making. I will dismantle everything. All right. Now see, these are the three inputs. I will take first variable to the first input of OR gate, then second variable to another input of the OR gate, and this third variable you can see here to the third input of the OR gate. All right. Now what I will do, I will take output of the OR gate. This is the output of the OR gate. You can see that I am connecting to a NOT gate. This is a NOT gate input. Okay, and output of the NOT gate I will connect to the anode of this LED. So you can see here that what we are supposed to do, we have to make OR of A, B, C. We have to take their complement. So that's exactly what we have done here. We have taken the output from the OR gate, that is from this point. That particular wire is going here, that is the input of the NOT gate, and the output of the NOT gate is directly connected to the LED anode. Fine. So now I will put the switch on, and now you can see the condition, this inputs, right? At this condition you can see all the inputs are now low. All the inputs are at logic low status. The output is high. Let us look into the truth table. You can see all of them are low. The output is high. Now you can see for any other condition the output is low. Any other condition, you can see I will go for two of them. I will go for two of them. Sorry. I will go for two of them. Now you can see nothing is happening. So we can see that in earlier case, these two columns, this column and this column, they were exactly showing us the same result, and here also this column and this column, they are exactly showing us the same result. So it is now verified that whatever DeMorgan's first theorem and second theorem states, they are perfectly correct statements. So this is all about proving DeMorgan's first and second theorem. Thank you, and we will meet in the next session.